So the next set of equations all involve temperature. So we need to start with a little bit of information about how we represent and measure temperature, and something called absolute zero and the Kelvin scale. And then we'll move through the next set of calculations, formulas, gas laws called Charles's law, Gay-Lussac's law, and the combined gas law. So when we measure temperature, what we're really measuring is essentially an average of how fast all the particles are moving. So the faster they're moving, the higher the temperature, which if you think about in terms of solid, liquid, and gas, solid, they're not moving very much. The particles are locked in place. That's the coldest of the three states. A liquid state is when they're given more motion, more energy, and they're allowed to move. So you heat them up, you give them more energy, or you have more energy, which means they're measuring a higher temperature. And then as you continue to increase the amount of movement, increasing the temperature, you eventually get to the gas state where they're flying around all over the place. And if we look at temperature being a measurement of motion, then there has to be a point at which you slow down, slow down, slow down, eventually stop. And if temperature and motion are connected, then the lowest possible temperature is when there's no more kinetic energy. That is called absolute zero, the lowest theoretical temperature possible. And the value of that number is negative 273 degrees Celsius or 0 Kelvin. So Kelvin is the scale based on absolute zero. There's no negative Kelvin. It starts at absolute zero and goes up from there. If you were converting Celsius into Kelvin, it's degrees Celsius plus 273 equals Kelvin. So whatever number you're given in Celsius, you add the number 273 to it, and that gives you Kelvin. You have to always do the temperature in Kelvin when you're doing these formulas. You have to convert from Celsius to Kelvin first, do the equation, and then if you have to convert back to Celsius at the end, you'd subtract 273 from your answer for temperature. You can't do the equation and then convert the temperature afterwards. It doesn't work that way. So Charles' law, now we have a constant pressure, which means unlike Boyle's law, we're taking pressure out of the equation, and we're looking at the relationship between volume and temperature. This is what's called a direct relationship, which means they go in the same direction. If the volume increases, the temperature increases. If the temperature decreases, the volume decreases, assuming you hold a constant pressure. So the formula looks like this: volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. And just like we had in the last set of formulas, we're going to be given 3 out of the 4, solve for the missing variable, and that's how we're going to do these problems. So we have a helium balloon with a volume of 2.32 when the temperature is 40 Celsius, and then if the temperature increases to 75 Celsius, what would be the new volume? So here is volume 1. Here is temperature 1. Now that's in Celsius, so we're going to have to convert that. This is temperature 2. Again, that's in Celsius, so we need to convert. So for the first one, for the first temperature rather, we're going to do 40 plus 273, which is 313 Kelvin. That's the number we're going to put into the formula. Down here we've got 75 plus 273, which comes out to 348 Kelvin, and that's the number we're going to use for T2. So we plug these in. Our first volume was 2.32 liters, divided by our first temperature in Kelvin is 313. That equals our second volume, which we're looking for, divided by our second temperature, which was 348 Kelvin. So if we rearrange the equation to solve for V2, you could either divide and then cross-multiply, or cross-multiply and then divide. It's up to you. But we end up with 2.32 liters times 348 Kelvin divided by 313 Kelvin equals V2. So we're going to carry that over to the... Okay, here's where we left off. When we do that math out, we get an answer of 2.58 liters. We said that temperature and volume go in the same direction. The temperature went up from 313 to 348, and the volume also went up from 2.32 to 2.58, so it follows the rule. So the next law in this set is called Gay-Lussac's law, and what we're doing here is we're swapping volume for pressure, but the relationship between pressure and temperature is the same as it was for volume and temperature. So if the pressure increases, the temperature increases. If the temperature decreases, the pressure decreases. So again, have to make sure we're always working in Kelvin for temperature, but otherwise we're going to solve these problems the same way as we did the Charles law problems. We're getting 3 out of the 4 numbers, plug in our numbers and find the missing piece. So we have a starting pressure of this canister of 5 atmospheres, a starting temperature of 25, so I'm going to do 25 plus 273, always convert to Kelvin, that's 298. That's the number I'm going to use in the formula. And then the temperature drops, rather, to -10. So if I do -10 minus, or plus rather, 273, I get 263 Kelvin. That's my temperature 2, T2. And I plug those numbers in. So my starting pressure is 5.00 atmospheres. My starting temperature was 298 in Kelvin. And that equals pressure 2, which I need to find, divided by temperature 2, which is 263 Kelvin. Rearrange that. It's 5.00 times 263 over 298 equals P2. So here we are here. When we solve that, we get 4.41 atmospheres. It's worth noting in these problems, if you're solving for temperature, then the answer is automatically in Kelvin. So you don't need to convert it if that's the answer that the value that you're looking for. So if you've got temperature 1 in Kelvin and you solve for temperature 2, it's automatically in Kelvin. You don't need to solve. You don't need to convert that, unless the question specifically asks you to do Celsius, in which case you'd go Kelvin to Celsius by subtracting 273.